The maiden flight of the X-59 QueSST isn't the launch of a production airliner or even a prototype in the traditional sense. It's the issuance of a passport for all aviation, granting it the right to re-enter the supersonic passenger transport niche. The half-century-long veto on supersonic flight over continents was born not so much from political will as from the shockwave that turned every flight into an acoustic conflict with the city. However, today the X-59 has proven that engineering can master even the most elemental forces of nature. But how did the Lockheed Martin team manage to tame the sonic boom? And why will QueSST's success reverberate throughout the industry? That's exactly what we're about to tell you right now. When the last Concorde touched down in 2003, a hush fell over aviation. Not just an acoustic one, but a symbolic one as well. Supersonic flight was gone, replaced by efficiency, comfort, and subsonic airliners. But in just over 20 years, the world has changed dramatically. Where decades of aerodynamic experiments were once required, digital simulations now reign supreme. Artificial intelligence has become an integral design tool, and materials have acquired properties that would have seemed like science fiction specialists back in the early 2000s. The X-59 QueSST, also known as Quiet Supersonic Technology, is an American experimental supersonic aircraft being developed by the Skunk Works division as part of the Low Boom Flight Demonstrator, LBFD, project. However, it wasn't a random experiment either. This craft is a direct descendant of the legendary NASA X-planes, often referred to as the Flying Hypothesis series, with which the United States tests the future before it even arrives. In 1947, it was the X-1 that first broke the sound barrier, the X-15 that soared to the edge of space, the X-29 that flexed its wings to counterbalance stability, and the X-43 that's remembered for its hypersonic record. Each of these iron birds was outstanding in its own way, and the X-59 will definitely be no exception. Looking back at history, even in the 1960s, it seemed that supersonic aircraft would soon become the norm. The United States was developing the Boeing 2707, Europe was building the Concorde, and the USSR was toiling away on its Tu-144. In 1964, the Federal Aviation Administration, FAA, together with the military, conducted a large-scale experiment in Oklahoma City, Operation Bongo 2. During this, 1,253 sonic booms were generated over 6 months, or about 7 booms per day. The objectives of the experiment were quantify aspects of transcontinental supersonic transport, SST, in relation to the city, measuring the impact of impacts on structures and public attitudes, and further development of standards for impact prediction and insurance data. The result was complaints from 3% of the population, or about 15,000 people, of whom 9,594 complained about damage to buildings, and 4,629 filed formal claims for damages, mainly for broken windows and cracked plaster. After the FAA rejected 94% of all claims it received, public anger was unabated, and by 1966, nationwide anti-sonic boom campaigns began to have a significant impact on U.S. public policy. This subsequently resulted in the cancellation of the Boeing 2707 supersonic passenger airliner, and in 1971 led to the complete withdrawal of the United States from participation in the development of SST projects as such. Since 1973, the United States has banned flights above Mach 1 or 761 miles per hour, except under special testing authorizations, and supersonic flight over land has become extinct. The same Concorde was only allowed to fly supersonic over the ocean, and for arrivals and departures in the United States, it was allocated specially limited routes and speed limits. However, the more players interested in supersonic and hypersonic transport appeared on the horizon, the more obvious it became the realization that the rules needed to be revised. Moreover, in June 2025, U.S. President Donald Trump signed an executive order directing the FAA to lift the ban on civilian supersonic flights over U.S. territory. To understand what makes the QueSST concept unique, let's quickly review what a sonic boom is. Consider a boat leaving diverging waves in its wake. An airplane does the same thing, only in the air. While its speed is below the speed of sound, the pressure waves disperse easily. But as soon as it accelerates, they begin to pile up, as if the boat were to jump on the waves at breakneck speed. At some point, these waves combine to form a sharp pressure surge, a shock wave that moves not only forward but also downward. That's why on the ground we hear it all as a double shock, first from the front of the plane, then from the rear. This sound, reminiscent of an explosive bang, is a sonic boom. The loudness of these impacts is measured in PLDB, the perceived noise level. And here's where things get interesting. While the Concorde had a sound level of 100 plus PLDB, like thunder, the X-59 engineers were determined to reduce it to 75 PLDB or even lower, which is comparable to a car door slamming. This was made possible primarily by the unique design of QueSST. It features a long, thin nose, accounting for approximately 1/3 of the overall length of this 99.7-foot aircraft. The wingspan, incidentally, is similar, around 29.7 feet. The idea of making the boom quiet emerged long before the X-59's preliminary design began in 2016. Back in the 2000s, NASA decided there was no point in fighting the shockwave. Instead, they needed to learn how to simulate it. The idea was incorporated into a joint experiment with Northrop Grumman, the Shaped Sonic Boom Demonstration, SSBD, which redesigned the F-5E fuselage to demonstrate the feasibility of generating a sonic boom and reducing the associated damage. After measuring 1,300 recordings, some of which were made inside the shockwave by the pursuing aircraft, SSBD demonstrated a reduction in sonic boom by approximately one-third. The years 2006 to 2007 saw the success of the Quiet Spike program, a collaboration with Gulfstream Aerospace. A telescopic 24-foot-long composite spike was installed on the nose of a NASA Dryden F-15B testbed. It created 3 small shock waves that traveled parallel to each other and reached the ground, producing less noise than the typical shock waves generated by the nose of supersonic jets. Moreover, the Quiet Spike not only confirmed the idea of a silent sonic boom, but also doubled the number of flights performed by the SSBD. Of course, this wasn't a switch to quiet mode, but it proved the principle that well-thought-out geometry of the fuselage and nose affects the shape of shock waves and therefore the volume on the ground. At the same time, the toolkit grew, from methods for calculating and predicting the propagation of booms to the PLDB loudness scales themselves, and the more accurate the measurements became, the clearer the target of 75 PLDB on the ground became as the bar for acceptable quiet supersonic sound. So here we are, with direct evidence of the sonic boom generating capabilities of the X-59, an aircraft capable of flying at Mach 1.42 at 55,000 feet, more than twice as high and nearly twice as fast as the conventional airliners we're accustomed to. This 300-pound long, hollow-nosed behemoth is powered by a modified General Electric F414 GE100 engine, which has proven itself on the American Boeing FA-18EF Super Hornet, the Swedish Saab JAS-39EF Gripen, and even the South Korean KAI KF-21 Boramac. With afterburners engaged, it delivers 22,000 pound-feet, 98 kilonewtons of thrust, to the Quest. NASA officials emphasized that the changes they made to the X-59's propulsion system included new engine management software and a modified fuel line. Other parts may look familiar, and for good reason. The X-59 borrowed its canopy and ejection seat from the Northrop T-38 Talon, its landing gear from the General Dynamics F-16 Fighting Falcon, its control stick from the Lockheed F-117 Nighthawk stealth fighter, and its life support system from the McDonnell Douglas F-15 Eagle. After all, NASA wanted to prove the possibility of a quiet boom, not a quick waste of taxpayers' budget funds. Thanks to these measures, the supersonic aircraft didn't become prohibitively expensive, and the contract signed in 2018 between Lockheed and NASA for the construction and delivery of the QueSST demonstrator was worth approximately $247.5 million. However, bringing the aircraft from the drawing board to actual flight cost NASA more than $518 million. Looking at the X-59's appearance, the following question immediately arises. What does the pilot actually see? Well, the pilot's positioned in the middle of the plane with no forward-facing windows and must rely entirely on NASA's specially developed External Vision System, XVS, during flight. It consists of a 4K camera, a flight vision camera, FVS, and synthetic vision. Using 4K video from the external cameras as well as comprehensive terrain data, the system creates a digital virtual head-up display for the aircraft. The EVS 3600 multispectral imaging system, built by Collins Aerospace and located just beneath the QueSST's long nose, helps inform the pilot of the aircraft's surroundings. The company also supplies the ProLine Fusion cockpit avionics, which displays the boom's position on the ground, and the Enhanced Vision System, EVS, which improves visibility at night and in poor weather conditions using infrared cameras. You can't see very clearly through glass when you look at it at a very shallow angle, and so you need to have a certain steepness of the view screen to have good optical qualities, and that would develop a strong shockwave that would really corrupt the low boom characteristics of the airplane, stated Michael Buonanno, the air vehicle lead for the X-59 at Lockheed Martin. When selecting materials for the QueSST structure, the Skunkworks team relied on aluminum alloys, although the rudder and supporting surfaces were made of composites. The tail unit was made from titanium alloys, taking into account the sensitivity of critical sections of the future supersonic aircraft's body to thermal loads. Additionally, the X-59 marks the first project in Skunkworks' extensive portfolio to utilize Electro-Impact's new high-precision and highly automated robotic drilling and tapping capabilities, powered by combined operation, bolting and robotic automatic drilling, Cobra robots. These machines drilled over 7,519 holes into the X-59 structures at a rate of 1 hole every 21 seconds, and only 23 of them had to be re-drilled. Perhaps it's precisely because of this high degree of automation in the development process that Lockheed and NASA have repeatedly noted that digital engineering and modern methods of working with materials have made the creation of the X-59 many times easier than if they'd undertaken a similar project 30 to 40 years ago. Testing of the apparatus and ground equipment started with a self-powered taxi in mid-July 2025 and continued with ground tests involving the F-15B by the end of the month. After the 2020 flight tests were postponed due to the COVID-19 pandemic and then postponed again in 2023 due to technical issues discovered in 2023, many fans were predictably delighted when media outlets began vying with each other to share videos and news of QueSST's first successful flight in October of this year. According to NASA, the X-59 flew at a lower altitude, around 240 miles per hour on its first flight to test systems integration, and further tests in the second phase of the QueSST program are planned to increase these speeds incrementally until it reaches 761 miles per hour at 55,000 feet. The third and final phase will be a community response study, which will involve flying the X-59 over various areas of the United States. Residents of these areas will send feedback on noise levels, and specialists will be able to come to specific conclusions, making minor adjustments to the X-59's design or its speed characteristics if necessary. This aircraft's a symbol of collaboration between NASA and industry. It's not looking to break any records, but its significance to the industry seems far greater than many machines of the past. You think the joint efforts of NASA and Skunkworks will be able to restore humanity's right to supersonic travel? Share your thoughts in the comments below. And if you enjoyed the video, please leave a like, subscribe to the channel, and hit that notification bell for more content like today's. Thanks for watching, and we'll see you in the next one.